Okay, hey guys, we are looking at the notes called static charge and Coulomb's law. This is going to be the first lecture for electricity and magnetism unit and our first flipped unit. Okay, so make sure you have out these notes in front of you, either to write on, you've printed them out and you're going to write on them, or you have them in Notability and you're watching the video on a different device. Okay, goals for the day, hopefully after today's lesson and the demos that we will do in class, you'll be able to describe the basic properties of electric charge, you'll be able to create a positive and negative charge on a specific material, and you'll be able to calculate electric force using Coulomb's law. Okay, we're going to go through a few of the basics here about charge in general, and then we'll go ahead and do an example that will help you with the problems that we'll practice in class. Okay, so let's get started here. All right, so electric charge comes from the electrons or the absence of electrons in a material. So what that means is that if there are more electrons than protons in a material, then we consider that material to be negatively charged. If there are less electrons than protons, we would consider that material to be positively charged. The reason it seems opposite, more electrons, negative charge, less electrons, positive charge, is because electrons are charged negatively. Okay, so more of them means negative charge. All right, electrons have negative charge, protons have positive charge. The magnitude of those charges are the same. Okay, so they have an equal amount of charge. It's just that one is positive, one is negative. That's the only difference. We say the magnitude of that charge is called E. Okay, that's specific for protons and electrons. Okay, if we're talking about charge in general, we usually use the letter Q for charge. Okay. All right. So in any process, electric charge is conserved. So it's sort of like energy and momentum that we talked about earlier in the year. And so we cannot lose any electric charge. The amount of electric charge in the universe does not change. So we can't lose it. It basically just gets transferred from one material to the next. Okay, so it will never change. Normally, electric charge is transferred when electrons leave the outer orbits of the atoms of one body. So they would leave that body positively charged, and they move to the surface of another body or another material, causing the new surface to gain a negative net charge. So if negative electrons, they move from one to another, the one that they move to will become negative. The one they move from becomes positive because they would have less electrons. This is how we get electricity. It's basically just the flow of these charges. Okay. So electrons have a charge of negative E, protons have a charge of positive E. Okay, E is just the letter we use for the charge of an electron or a proton. Okay, and that number is 1.6 times 10 to the negative 19 coulombs. Coulombs is the unit that we're going to use for charge. Okay, and it's named after a person, Charles Coulomb, so it's always capital. Don't use little c. Okay, little c is for the speed of light. Big C is coulombs, and it's how we measure charge. Okay. Now, I'm sure you've heard this part before, but I'm just going to go back and repeat this for you. Similarly charged objects or like charges repel, okay? And oppositely charged objects will attract. This is where we get the saying opposites attract. Okay, so a positive charge and a negative charge will be attracted to each other, and a positive charge and another positive charge will push each other away. Okay, and same with two negative charges will push each other away. Okay, this is just sort of a little picture for you. A positive charge its electric field will be in the direction away from the charge, whereas a negative charge will have an electric force or field coming toward it. The value of the electric field that just tells you the force that some object would feel if it entered the field. So if there's an electric field, then if an object entered that field, the electric field is what is just the force that object would feel. Okay, it tells you the direction of the positive charge would go if it were placed in that field. Okay, we'll talk more about that when we get into class and do the demos. Coulomb's law. This is the most important part of this lecture. Okay, Coulomb's law describes electric force. Okay, the electric force is a field force like gravity. So that means that two things do not need to be touching in order to feel an electric force between them. It's a field force, and so it's just based on the amount of how close they are together and how strong their charge is. Okay. The equation for the electric force, we use F for the electric force, is equal to K. I'll explain what K is in just a moment. Q1, Q2 over R squared. And really, this is the absolute value of these charges. Okay. And the units will be coulombs. Now, K is the Coulomb's law constant, okay? And it is always 9 times 10 to the 9th. The units are kind of weird, but it's newtons times meters squared over coulombs squared. Okay, basically that unit is just to make sure that this comes out in newtons. I'm sorry, I messed this one up. The force actually comes out in newtons, not coulombs. Sorry about that. So go ahead and fix your notes. This should say newtons. Force is always measured in newtons. Sorry about that. Okay, so it's just to make sure that this force comes out in newtons. Okay. Q is the charge. Okay. And R is the distance between charges. Okay. And this equation is basically what's the electric force from one charge on another. Okay, and that's why we have two charges here. Okay, so we're going to go ahead and solve this example together. I've chosen this example because I believe it will help you the most with the problems we're going to do in class. So we're going to go ahead and solve this one. I want you to go ahead and get a blank sheet of paper for me because you will probably need a little bit more space than is given here on this note sheet. So I'm going to go ahead and set up. Why don't you grab a separate sheet of paper? Okay, so here we go. We're going to go through this problem together so you get an idea of how to solve problems like this. Okay, so sphere A is located on the origin. Now, in these problems, they're probably going to give us a location on an XY axis at first. Not all problems will give you it as an XY coordinate system, but this one is. So that's what we're gonna draw. So sphere A is located at the origin. Okay, I'm gonna write A next to it, and has a charge of positive 3 times 10 to the negative 6 coulombs. I'm just gonna put a plus sign near it just so I remember that it's a positive charge. Okay, and then over here I'm gonna say that the charge of A is equal to 3 times 10 to the negative 6 coulombs. Okay. Then it says sphere B is located at positive 0.7 meters on the x-axis. So I'm going to go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. I'm going to say that's 0.7 meters. I'm going to say that's where sphere B is. And sphere B is located there and has a charge of negative 4.2 times 10 to the negative 6 coulombs. So I'm just going to put a little negative sign next to it just so I remember that it's negative. Okay. And then sphere C is located at 0.9. So that was 0.7, so 0.8, 0.9 meters along the positive x-axis and has a charge that's positive. So I'll put a positive and I'll put C. And QC is 3 times 10 to the negative 6 coulombs. Okay, so now I have my picture. So before you start, what I want you to think about is that A and B are repelling each other. Attracting each other because they're opposite. Okay. A and C are repelling each other because they're like charges. They're both positive. And B and C are attracting each other because they're opposites. Okay, so you should just kind of keep that in mind of what's going on with the forces. Okay. Now our question says determine the net force on sphere A. So we're concerned about how these two charges are pulling on sphere A. So if you think about it, B is pulling sphere A toward it. C is pushing sphere A away from it. Okay, so we're going to figure those out and I'll let you know how we should do the signs, but for now just kind of keep that in mind conceptually. So on sphere A, that's what we're worried about. Okay. Now, we're going to have to do two different equations because we can't put three charges in this one equation. So first I'm going to do the force of sphere B on A, and we're going to note it like that. And the equation would be K, Q, A, Q, B, doesn't matter the order, over r squared, where this is the absolute value of these charges. Okay, and when we plug in, we're going to get 9 times 10 to the ninth. Over here we have QA, which is here, which is 3 times 10 to the negative 6. QB is negative 4.2, but it's absolute value, so don't plug in the negative. We'll worry about that later. Over r squared, which is the distance between A and B. So it's 0.7 squared. Don't forget to square it. Okay, I'm going to plug this in my calculator in front of you so that you can see the first one, and then from there I'll just go ahead and do it on the side here. So I have 9, I'm going to put this in parentheses, 9 times 10 to the ninth times 3 times 10 to the negative 6 times 4.2 times 10 to the negative 6. That's my top part. And then I'm going to divide that by 0.7 squared. And I end up with a force of B on A of 0.231 newtons. Now, for the sign, we're going to look at A and B. Since they are opposite charges, they'll attract. So A is going to be pulled toward B. Okay, they pull toward each other. So A is getting pulled to the positive direction, so I'm going to leave that positive. Okay, now for C on A, and remember we're doing both of these charges on A because we're worried about the net charge on sphere A. Okay, if I was worried about the net charge on sphere C, I would do B on C and A on C. Okay, but we're worried about A. So C on A is going to be the same equation, so we'd have 9 times 10 to the ninth, QA, which is 3 times 10 to the negative 6, QC, which happens to be the same thing, over, and then their distance would be 0.9. Okay, and I'm going to go ahead and plug that into my calculator. Okay, so for force of C on A, I got 0.1 newtons. Now, if we think about the force of just C on A, because they're like charges, they're both positive, they're going to repel. That means that C is going to be pushing A in the negative direction, and so I'm going to make that force negative. Okay, now for the net force, remember when we went way back to when we did net force on objects with Newton's laws, we said that the net force was the positive forces minus the negative forces, and it's the same idea here. So here we're going to have the net force is going to be the positive force, so 0.23, minus the negative force, so 0.1, and we're going to end up getting, let me pull this down a little bit, 0.23 minus 0.1, we get 0.13. I probably could have just done that in my head, but we get a net force of 0.13 newtons. Okay, for sphere A, which means that it's being pulled in the positive direction with a force of 0.13 newtons. Okay, so we're going to talk more about this in class. You're going to solve some problems on your own in class with this. We'll do some demos, but make sure that you watch this enough times that you understand how I got those answers, and write down any questions. We'll go over at the beginning of class any questions you had about the notes. Okay, all right, see you guys on Wednesday.